Today we're going to be solving at a distance. This is what it looks like. In this problem, we're given a word 1, and we need to perform 3 operations on it. Add a letter, subtract a letter, or replace a letter in sequence, and try to find the minimum number to get from word 1 to word 2. Let's draw this out. We're going to use the example in the problem because it was a pretty good one. Our word 1 is horse, and we need to turn it into word 2, ROS. So how can we do this? So let's write out the word horse. The first thing we might notice is that there's a lot of repeated letters between ROS and horse, so we probably want to take advantage of that. For example, we could take the letters O and S. Note that we can't use all the letters ORS and to map to ROS because they don't appear in the same order, and there is no kind of swap operation in this problem. So we can only take the ones that are properly in order to recycle them. So for this one, we're going to take O and S. So what do we do with the rest of the letters? Well, from horse, the first thing we need is an R at the front for ROS. So we can replace the H with an R. That becomes RORSE. The O is already there in the right place. We go to the R, we just need to remove that. The S is correct. We go to the E. Now we have ROS. That took a total of 3 operations, and that's the correct answer for this problem. So as we start thinking about how we might do this more generically, I want to bring up another example of recycling letters. Let's recycle R and S instead. So again, we start with horse. Remove the H, O-R-S-E. Remove the O, R-S-E. We can't do any kind of replace for the O, unfortunately, because there is no letter between R and S for us to replace. So we just have to add the O in there. And then finally, remove the E. So this actually took us 4 operations despite sharing recycling 2 letters like we did for the first one. The reason I bring this up is because at first glance, and what I did too, is that it seemed like it was just a matter of finding some kind of intersection between word 1, word 2, and then doing some kind of combinatorics or mathy thing, figuring out the properties to end up with the solution. But after quite a long time of working, I can tell you that that doesn't really work. So instead, we're gonna approach this problem with a smart brute force. The first interesting thing to note is that there is no brute force for this problem, or at least that I could find. What I want to do with a smart brute force is to set forth some properties to narrow down our problem space so that it's not so difficult to think about and kind of force our way through the number of solutions or all possible solutions in that space instead. The 2 properties I want to, for the record, for those who know the terminology, we're going to be using dynamic programming, which I usually think of as a smart kind of brute force. The properties I want to surface for us to talk about that help us narrow down our problem space are number 1, specifying an order of operations does not affect optimality. This is the most important one, and it's going to take a second to explain. As we mentioned, when I was talking about the brute force, you could do these operations in any order you want. You could remove E, remove R, replace H, the reverse of that, anything in between, and you still end up with the optimal number. So you can do these in a lot of different orders. Taking that one step further, you could do these operations, I'm going to assert, you could do these in any order you want. So all possible orderings of those operations, and you would still get the same optimality, the same result. And therefore, it's still the most optimal result. And as a very short proof of this, you don't ever have any 2 operations dependent on each other in the most optimal solution, because here's an example of a dependent set of operations. You add A, and then you replace that A with a B. You could simplify that to just add a B. In any optimal solution specifically, you would never have this chain. And so for the optimal solution, we will only have independent operations, and we can put them in any order for reasons specified. So that's property 1. And what this means is we're going to be addressing, we're going to be And what this means is that we're just going to choose a specific order to apply these operations, specifically front to back. The second property is just a restatement of the problem. The ordering of word to matters. So it has to appear in ROS. It can't be ORS or RSO or anything like that. So at a high level, what property 1 tells us is that we can specify any order we want to perform these operations, and it will still be just as optimal as long as we find the optimal solution, one optimal solution. In conjunction, or when we apply this along with number 2, that the ordering of word 2 matters, that means that in whatever order we consider word 1, we have to consider word 2 in a corresponding order. So for example, horse and ROS. If we go from left to right, from H down to E for horse, that means we have to go R to S for ROS. So we've defined the problem space. We're going to start with horse, and we're going to go letter by letter, HORSE, and then transform this eventually to ROS, left to right. So let's actually solve how we might do this. So at every step, again, we're starting here at the first letter H. We have 3 options. We can subtract a letter. We could, and again, following property 1, that means it's going to be the leftmost letter H. We can add a letter R, like following both these properties together. So R, H, O, R, E, S, E. That's what I meant. We have to start at the left of ROS because of these 2 properties. Or we could replace the H with the R, again, for the same properties, because of the same properties. I wrote this in this grid very intentionally because this is how we're going to proceed along to get to ROS with our dynamic programming solution. This is going to be our grid. So how I'm going to specify is every time we move right, we're subtracting a letter from horse or word 1. And when we go down, we're going to be adding a letter from ROS or word 2. Specifically minus H in this column, minus O, minus R, minus S, minus E, and then plus R, plus O, plus S. Let's write out a couple more cases. We minus the O, minus the R, minus the S, minus the E. Underscore just means there's nothing there. ROHORSE, and then ROSHORSE. Now let's write a little bit of the middle grid in. We subtract the O, so we get RRSE. Similarly, for this grid down here, we add an O, so this becomes ROORSE. And then for this item here, we could go any number of ways, but I'm going to choose to add an O to RRSE to get RORSE. And you could keep going, and eventually what you'll get to is ROS. I'm not going to write out everything, but that's how you do it. How do we apply min edit distance to this grid? Well, let's start at the base case, just the word horse. So for horse, to get the horse at this top right here, it takes no edits, 0 edits. In order for horse to get to ORSE, 1 column to the right, that just takes a subtraction of the H, like you can see up here. So that's 1 operation. Similarly, RSE is just 1 more subtraction, and so on. On the first column, going down the rows, it's a similar story. Add an R, add an O, add an S. Now the interesting part is, how do we fill out the middle? Let's take RORSE as our example. We can get here in 3 ways, like we said. We can add a letter, subtract, or replace a letter. So let's start with subtract. We could subtract the R from, start with add. We can add an R from ORSE. That takes a +1 operation, so that would be 2. We could subtract this letter from R horse. That's another operation, that's also 2. Or we could replace the H from horse with an R. That's 1 operation, but we started from 0, and so that's just 1 operation, and so that should be the min edit distance of RORSE. let's fill out a couple more. RRSE, similar story. Add an R, subtract an O, or replace the O with an R, and the minimum of these is 1, add 1 is 2. ROORSE is subtract O, add O, subtract H, replace H, and it's again minimum edit of 2. From RRSE to RORSE, we can add an O, we can subtract an O, or we can replace an O with an O, which I guess we could do, but really that's more optimally just a no-op. We just don't do anything with that. And so this is a very special +0 case. And so this, I didn't leave a lot of space, but this is actually a min edit distance of 1, taking no extra operations from the last RORSE. So those should be all our cases. I'm not going to walk through all the way down manually to ROS. That's just way too many. But I think we can finally now code it out. Okay, so using Python as normal, we just need to translate that grid that we just walked through into code. So I'm going to call it min distances. Pretty appropriate, I think. Let's create the grid of the appropriate size. So we want each row to be length of word 1 plus 1, because in the original example, you can see here, we have the number of letters of horse, but we also have an empty space because we need to do that number of subtractions. So we need word 1 plus 1 number of spaces. And just to jump ahead a bit for ROS, we also need that for similar reasons. So each row, we're going to make word 1 plus 1 length. And then for the number of rows we need is the length of word 2 plus 1. That's our grid. The next thing we did is we filled out our base cases. So for I in range, length of min distances. So this is our first column. And it just equals I because it was each addition. So horse, R horse, RO horse, etc. And then similarly, we know this first row is defined, and we go along this first row. Okay, we have the grid, we have our base cases. Now we need to define the meat, the part where we actually do the min distance calculation. So for W2, meaning the index of the second word, in range 1 to length of min distances, 1 because we filled out the zero column already. And then for W1, meaning index of word 1, in range 1 to length of min distances 0 for similar reasons. So in the example, you could see applying the 3 operations, add, subtract, replace, took the grid above, the grid to the left, and then the grid up diagonally for us to solve. So we need those 3 grids filled out in each case. The way we're iterating now, we're starting with this grid item here, and we're going to the right, and then we're going to the next row to the right, etc. So you can see in each case, these 3 are filled out, and then we fill out this grid, we go to the next one, these 3 filled out, go to the next one, these 3 filled out. So we should be covered. Oh, and finally, when we get to the next row, these 3 are filled out, etc. So we should be covered in all cases for our DP to not run into any none scenarios. So now that we have our loop and the base case is filled out, let's do the final piece, which is just take the min edit distances and use them to find out our current min edit distance. So we have 3 possibilities. Add word 2 letter, so add an R, O, or S. So this would be equal to min distances of 1 column prior, or sorry, 1 row up, plus 1. We could subtract a word 1 letter, HORSE, and for this one, we go up 1 column. or we can replace a word 2 letter with word 1 letter. A little bit verbose, but it's clear. But before we take this in our minimum operation, we want to check the special case that we were saying where the letter we're replacing is actually equal to the letter that we're adding back. So if word 1, W1, equals word 2, W2, but one thing to note is that these W2 and W1 are incremented by 1 over what they actually are in terms of the word index. So we should subtract 1 from both of these. So in the case that word 1 letter equals word 2 letter, then replace word 2 letter with word 1 actually just equals min distances of W2 minus 1, W1 minus 1. AKA it doesn't actually take an operation. And if it doesn't, then it's what we said earlier. We fill out the item in our grid. It's the minimum of add word 2 letter, sub word 1 letter, and replace the word 2 letter with the word 1 letter. This loop should fill out our whole grid. And finally, we get our solution, which is the very last item, the last row, last column in our grid. We return that, we submit this, and it solves the problem. And of course, the last thing is runtime. So what is the runtime of this problem? Well, if we look at this grid here, it's horse long, H-O-R-S-E, meaning the length of word 1. It's R-O-S tall, meaning the length of word 2. And in our code, you can see that we just do a bunch of constant time operations each loop. So it's just 1 times m, the length of word 1, times n, the length of word 2. So runtime is O of m n. Okay, and that's it.